Hi, this is Sung, the Principal and Director of Sky Academy, and we're drawing towards the end. We're on the home straight of this topic of geometrical applications of calculus, and in this particular episode, we're going to look at a concept called primitives or antidifferentiation, or finding the antiderivative. Now, in future chapters, we're going to see this whole new world of working backwards in calculus open up for us. So let's actually explore what finding the primitive or the finding the antidifferential or the antiderivative is all about. Okay, simply put, finding the primitive or the antiderivative is really just reversing differentiation. Okay, so just like division is the reverse of multiplication and subtraction is the reverse of addition, okay, finding the primitive or antidifferentiation is the opposite operation or the opposite function of finding the derivative. Okay, so the primitive, and it's written as capital F of x of a function small f of x, is the function that would make f of x the derivative of capital F of x. Okay, so basically it's like it's doing the reverse of differentiation. Okay, and there are some basic rules. So with differentiation of an x to the powered term, basically what you did was took the power, multiplied the power with the coefficient or up the front, and then took one off the power. When we're doing the reverse, finding the primitive, what we're doing is adding one to the power and dividing by the new power. Okay, so if you've got ax to the power of n as your original function, then finding the primitive of that is all about dividing by the new power and adding one to the power and dividing by the new power. Okay, where you've got a binomial expression to the power of n, all right, to a power, you basically raise the power of the binomial by 1, divide by the new power, and you divide by the differential of the inside. Okay, in this case, ax plus b, you're dividing by a as well. Okay, and for, it's kind of like the reverse of the chain rule, but if you've got a function to the power of n, right, multiplied by the differential of the function, the opposite of the chain rule, or the function of a function rule, allows us to raise the power of the function by 1 and divide by the new power. Okay, and the differential of the inside function will disappear. So there's some basic rules. These need to be committed to memory. You'll be using a lot of antidifferentiation in future courses, but it'll be dressed up as a completely different concept. Okay, concept known as integration. But I won't spoil the fun just yet. So just remember those formulas. In fact, I'll move out of the way so you can copy them down. Okay. And then we'll look at some examples on the board. Okay, so the first example is 3x squared plus 4x plus 7. What we're doing is we're raising each power by 1. So if we raise this power by 1, what we end up with is x cubed, and then we're dividing by the new power. All right, so 3 on 3 plus 4x, and we're raising that power by 1, which is squared, and dividing by the new power. And then with the 7, that's like 7x to the power of 0. So you raise that power by 1 and divide by the new power. And what you'll end up with is a function that looks like this. The primitive will be x cubed plus 2x squared plus 7x. Now, there is something that I must point out here, and that is, with the primitive term, you also have to add a constant. And the reason why you have to add a constant is if you were differentiating that and any other term with a constant on the end, by differentiating, you would get rid of the constant, okay? And so what this constant represents, this plus c represents, is the missing constant that got disappeared when we differentiated, okay? So we need to acknowledge that there was or may have been a constant there, even if the constant was 0, by adding a c to the primitive function, to the antidifferential, okay? So that's why it's very important to add a c. Now, I've done it in red because it is that important that you put the plus c there. Okay. Let's do the next example. In this example, we're going to see this is a binomial, so it takes on the form of ax plus b to the power of n. All right. In this situation, you raise the binomial by 1, so 3x plus 7 to the power of 12, and you divide by 12, but you also divide by your a term, which is 3. Okay. Yep. So your equation would be 1 over 36, 3x plus 7 to the power of 12, and of course, we do not want to forget this. We want to add a c on the end. Okay. And then the last one, what you'll notice is the differential of this, 2x to the power of 7, is 14x to the power of 6. Okay? So, this takes the form of this one here, okay, and g to the x is the 14x to the power of 6, which g dash of x, that'll disappear, and we're just left with the g of x, which is the 2x to the power of 7 plus 3, alright, to a raised power divided by the power, raised by the new power, okay, so 2x to the power of 7 plus 3, all to the power of 6, divided by 6. Okay, and that will be your answer, so long as we remember to add the c on the end. Okay, so that is primitives or antidifferentiation in a nutshell. If you didn't get it this time around, that's okay because we'll be covering it again in our next topic, all right? And it'll take on a whole totally different form, okay? But this is just getting our toes wet in the water with this particular concept. So have a go at practicing some questions, and I will see you in the next topic, in the next course. Thank you very much for watching.